Thank you. I'm just we said that we should be a little bit more free and flexible and have some informal discussions. I'm pretty flexible if you want me to cover some, because I'm supposed to give 3 talks.
You take requests.
Yeah, I accept requests. And I usually would thank the organizers, but instead I will tell you an anecdote, a real thing. So I was invited maybe more than 1 year ago, about 2021. I completely forgot about it. And then, and there was a message that the proposal was accepted, which I kind of looked through and forgot about it. And then I received this mailing list, eager algebraic geometry, and I start reading, and it says workshop about colon branches and double affine Hecke algebras. I'm like, what? It's really interesting. This is exactly what I want to learn. I should write to the organizers and try to get invited to the workshop. And I scroll to the bottom and it says, Anton Mellit mini course. I was surprised that I am already invited. And the second surprise was that instead of learning about it, I'm supposed to. Put me in a tough spot. But in any case, I hope I was asked to start very, very basic, and so I will start with very, very basic things. So first, maybe there is some kind of plan. In some way. There's sort of plan goes a bit in this direction, in the direction of complexity, but also it will go to some kind of okay. And then maybe I will draw some sort of picture, and then there are many different algebras. And to systematize them, we should probably divide them by the number of loops. So no loops, 1 loop, and 2 loops. But also they can be divided by there is another dimension, sort of. There is the number of deformation parameters. So if you have and then you can have no parameters. Then you can have Q, and then there's Q and T. So, and that's makes right. So
you think there's a difference?
Well, it's sort of just so it is increasing complexity. But this one is increasing number of loops. Just keep in mind that you can there are 2
Is there
unrelated
something in that top right corner?
Yeah, in each no no, maybe not. But yeah, I don't pretend to be. There's nothing here and here. Not as far as I know.
You may have third dimension as categorification level.
Right. There is another dimension. Whenever you have one of these algebras, you can also think about different ways to find the geometric interpretation for it. So the geometry can be of the following flavors. So possible geometry. One is I don't know, purely topological. So that's when you draw some diagrams, I don't know, and do some kind of pictures like this, and maybe look at these pictures inside some surfaces. Then there is K-theoretical. It's when you want to look at, let's say, vector bundles on spaces. Okay, and then there is another thing. Maybe constructible, yeah. So you have some space, some varieties. Variety, and so on. Actually, let's just keep it mysterious. So the point is that there are many different ways you can try to find the algebra in geometry. Okay, so before so the first thing to explain is that the beginning it's completely undeformed, and no loops. That's the first sort of. We already used several labels. So, what is the input to the story? I always work with type A, and even not just type A, but GLL. So let's fix some notations. So n is fixed. Then we will use the group G is GLN over complex numbers. I sometimes use I use C to denote the finite field. Is few elements. Q is a prime power. I will try to say when that will be the case. So this is the Lie algebra of G, and this is a n by n matrices. And right, so next then W is a permutation group of Sn. Well, maybe I can. Then I have various standard things inside G, and inside G, the Lie group and the algebra. So B inside G is upper triangular matrices, and T inside B are diagonal matrices. And then also in similarly, the Lie algebra is written as G minus direct sum H. This is kind of fancy H, and G plus, where this means diagonal. It means strictly upper triangular. And this is strictly lower triangular. So this is now let's what we want to study. We want to study representations of big G, of small g, of W, and so on. So let's to be able to kind of diagrammatic calculus. And it is useful, this diagrammatic calculus is useful to kind of study representations of all of them at the same time. I think this is, I think David was referring to, it was mentioned in David's talk. So again, here we have no. Let's first start to diagrams for SM. For W, right? So that's very easy. You have n dots on top and n dots on the bottom, and any permutation will be encoded by connecting the point on top to the corresponding wave phi is in W. Then 1 will be connected to pi of 1, 2 will be connected somewhere to pi of 2, and so on. And since clearly there is not, it's not important if for every crossing, it doesn't matter which line is over, right? Because we are dealing with permutations. We are also we can describe the permutation group abstractly using generators and relations. So we know that SM is sigma 1 generated by generators up to n-1 modulo relations. Sigma I square is 1, sigma I sigma j equals sigma j I, when I minus j even 1, and sigma I plus 1, sigma I equals sigma I plus 1, sigma I plus 1. So this is well known, and on the pictures it looks like this. So sigma I looks like a bunch of parallel lines, then 2 lines I and I plus 1 they cross, and then, for instance, this relation we have something like, if you take 2 lines and this equals, we just slide it over. Yeah, only the order of the lines is important. So okay, now let's talk about GLN. So this is a so we want to suppose we want to understand the representations of GLN. We are not supposed to think about like actual elements here, and what we should think about what is it? How does a representation look like? So what's the category of representations of this group, of this Lie algebra? And so let's say this is as a Lie algebra, and we want representations. And immediately you arrive at a natural assumption that if V is a V be a representation of the representation, then we should try to, for instance, maybe we want to study some infinite dimensional representations and so on. There is also this group G. We want to study representations, which we should think about them as the extent to the group. But usually that is too strong assumption. So, and maybe we don't even have the group at all, for instance, in the situation of Kac-Moody Lie algebras and so on. So from this point of view, but still the following assumption is very natural. So assume that representation H of H acts. So the action of H it can be integrated to the action of the torus. So lifts to an action of T. That's our assumption. Algebraic. And once there is an action of algebraic action of a torus, it is a basic fact that it's nothing else but the decomposition of V is a direct sum over characters. So equivalently, V is a direct sum of V, let's say W, where W is indicating how the torus acts. So every algebraic torus action can be diagonalized. And this is what I'm doing. W is going over the set of characters of. And in our case, since T is simply the diagonal matrices, so product of C star n times, this T star is Z to the n, and so V is simply graded by Zn. So that's what the assumption means. Now, how do we display this in a diagram? So whenever we have if V is such a representation, when we draw a line and put some points on it and put some numbers, so actually I need to be precise, I need n points, and I put the numbers a1 to an. So this for me means corresponds to V A. A is the vector of all the A's. So in my graphical calculus, this corresponds to the subspace, and pictures will correspond to maps. So elements of G will, and also, like, well, if you have an action of Lie algebra, then of course you have an action of the universal novelty. And on G there are certain pictures. So what kind of pictures can we have? Let's start now writing some explicit presentation of the thingies. So as a Lie algebra, we know that, so here is G. This is generated by elements. I denote EI, FI, HI. Here, I is from 1 to n minus 1, but here I is from 1 to n. Modular relations. And the relations are that, well, now it's a long list. The thing is that you should, well, EI corresponds to the matrix 0, 0, 1, 0, where this is I plus 1. That's all. And Fi is the same, but transpose. And Hi is similarly 0, 1, 0, 0. I. And now we can, so recall that H will correspond to, so this corresponds to the action of the torus, which means that this is just a gradient. Just the gradient. In other words, Hi acted on restricted to the space V VA is just AI times the identity of VA. So that shouldn't be so much interesting. So Hi, comma. Now, but yeah. So how does it interact, for instance, with EI? So Hi, comma EI is if you just commute the matrices, you will get EI, Hi, Fi is minus Fi, Hi, Ei plus 1 is minus Ei plus 1. Hi Fi plus 1 is Fi plus 1. And all other Hi, Ej, and Hi, Fj is 0. This is how so we completely understand now the commutation between H and E, and it simply encodes the relations like Hi, Ei equals Ei, Hi plus 1. So Ei has to increase the degree. So Ei has to increase Ai by 1. Similarly, and decrease Ai plus 1 by 1. And so on. Similarly, Fi does the opposite way. Now, what are the other commutation relations? Now I'm continuing writing the description of the Lie algebra. Another one is Ei Fi is 1. Sorry, what am I saying? Hi minus Hi plus 1, right? And others 0, meaning all Eifj. And finally, there is a cubic relation. So this is kind of trivial relations, grading, trivial. These are quadratic. And cubic relations, finally, that's the most interesting. And that's called Serre relations. Is that if you take, right, so Ei, Ej commute if they're far. Greater than 1. And that's still quadratic, sorry. Similarly for Fi. And cubic. Cubic relations. That if you take adjoint I square and you apply it to J to I plus 1, that's 0. So if you open this, and similarly for F's and when I and I plus 1 are interchanged. That's the conditions. So you can open this very, for instance, you have write it as follows. That's the okay. So now you can ask what is a good way to write pictures for these elements, and this is the naive way is it simply works. So pictures that whenever we have, so I always read pictures from top to bottom. Then EI, let's see. So we have this points labeled A1 up to AN, and then there is AI, and there is AI plus 1. And we want to do something. We want to, AI has to increase by 1 after this, and A plus 1 has to decrease. So the way to draw it on the diagram is to imagine that these lines are kind of thickness. So AI is a thickness, and then you simply split off one line of thickness 1, and you join it to this line. And yeah. Now what about FI? FI should be the other way around. So also you can say that there should be some duality which interchanges EI and FI. So it just flips the diagram like this. Okay. That's the, and then relations correspond to certain transformations. Some rules about how we can transform diagrams. And then what interesting point is that this calculus by those theorems that David mentioned, this calculus is theorem basically that if you wobble your diagrams, if you kind of view these diagrams in different ways, the result is the same. So this is invariant under say, I don't know, deformations of diagrams. And I don't know if I can prove that theorem, but so instead I will just maybe give you some examples. So examples. Yeah, I need more space for the examples. So what do I mean by deformation of diagrams? Imagine you have, for instance, these 3 lines. And I think this is just 1, 1, 1, 1. And then one thing you can do, you can first merge. No. Okay, first merge this one to here. Then this is applying E1. So there are n equals 3. Then now this has 2 and this has 1. Now, so I want my goal is to merge all of them together, but now I have to just this turns out to be a non-trivial move in this calculus. So, and this is precisely E1. So I forgot to say thickness 0 can be also omitted in the. So it's my convention. Thickness 0. Yeah, and right, and I forgot another thing that in this when I said that I will think about AI's thickness, I implicitly assume that they have to be non-negative. That's so we have another assumption, and that all AI's are non-negative, and that corresponds to the assumption that the representation is a polynomial representation. So V is and then later you will see why this is very natural, these assumptions. So, okay, so this is now E2, right? I have to take this position 2 and 3, and then what is acting between them is called E2. And then you merge this together, and this is E1. So can I draw this diagram differently? Well, you can have, right? So as I have the relation, right? So E1, this is E1, E2, E1. On the other hand, I know that 2 times this equals E1 square E2 plus E2 E1 square. So let's draw E2. E1 square. So first I merge this and this. Then I have to split off 1. And this is E1. And then I finally merge result here. So here in between, or sometimes nothing happens. So 2 times this diagram is this one plus plus 1 square. But now let's see, can we make E1 make sense of E1 square E2? So this is E1, but then there is no line here. Now the thickness here is 0, and then I cannot apply E1 again. So this is 0. This correction is 0. So we have just this identity. So this is how the calculus works. But yeah, I didn't. This is kind of example of a. But let's. What about the following? Suppose it is 0, 1, and 1. No, wait. Right. So for instance, take this and then do this thing like, and then like right here. So this seems to be like a trivial diagram. It should be identical. But if I think about this 0 is, but if this means E1 for me, so this is n equals 2 situation, and this is F1, right? So this diagram is F1 E1. On the other hand, let's check this. We can transform by the commutation relation as E1 F1 plus H plus H2 minus H1. So this diagram is 0. This corresponds to 0. 0 plus, and then this diagram, but H2 simply multiplies by 1 and H1 simply multiplies by 0. So this is just 1 and this is the identity. Okay. So here's an example of a diagram that I deform and I get the same result. And I hope this example kind of illustrates and you may start thinking that you can realize that it's a non-trivial theory. Let's now talk about relationship between. So we have representations of GLN and we have representations of SN. So GREPs or WREPs. Yeah. So is there some kind of overlap between these two worlds? And indeed there is an overlap. If we have V here, then we can look at the space where the torus acts just by weight 1, 1, 1, 1, 1, 1, 1. So then we take V A where A is so V 1, 1, 1, 1, 1 n times. Then so here this character 1, 1, 1, 1, 1 is invariant under the permutation group. Therefore, this weight space has to have an action of the permutation group because it's precisely the normalizer of the torus. So model of the torus. So right, this now is here. So at least one way we have some kind of a relationship we can try to play with. Now, grammatically, we had two. Both sides have diagrammatic calculus now, right? So if we have V and we draw some, we take 1, 1, 1, 1, 1, then according to our calculus, we should look at points with numbers 1, and the maps from here to itself are encoded by diagrams like this. And here now we have two kinds of diagrams. We can place here the Lie algebra diagrams, or we can use SN diagrams. What is the relationship? You can ask. Well, there is an explicit map. So we have seen. No, we haven't. No. Okay. So we have the following relation. If we have 1 and 1, and then we write E1. Let's write first merge them together and then split them again. That stands for F1 U1, right? Now we can check that F1 U1 is squared using the commutation relation. It's F1. It's F1, then in the end E1, and here I commute them. But the result will be 0 plus the following, plus H1 minus H2 E1, and this is 2. So this is 2 F1 E1. So you can guess how to relate the generators. So we write sigma I, that's Fi EI minus 1. Now this has spectrum 0, 2. So I subtract 1, I get spectrum minus 1, 1, which means it is the reflection. And then you will do a lot of pictures, draw a lot of pictures, and convince yourself to see that the sigma i's satisfy SN relations. Okay. For instance, the I sigma commutes with sigma j. If they're far, well, you just slide the pictures of it. But with I and I plus one, it is a little bit more work. But at least you can see that initial the GLN relations are cubic and the SN relations are also cubic. With degrees, can say. Cool. So now let's remind you how relate GLN, SLN, and put them in one diagrammatic calculus. Now I'm going to set C equals Q. Plus F cube. And now let's deformation. Remember, we are like now, we have no loops and we have no deformation. Now we're going to sort of kill that from here. Deformation, and here I will already start introducing some geometric motivation. Geometric motivation that you will see that you just do some trivial stuff to play some games and you get some deformation. So let's consider and yeah, so consider the let C be FQ and then X. Sorry, no, so V stands for C to the N. This is just a vector space, and then we are going to look at flags. So how do we put flags? So V0 will be just 0, and then it will be inside V1 and so on, VK. V M, and this is CN, and then these are subspaces, and so that you fix some vector XA, a vector of non-negative integers, and then you will have condition that dimension of VI modulo VI minus 1 is AI. So this collections of flags we call, this is called flag variety. It's usually denoted as G mod PA, but or we call the where PA. So it's actually the quotient of G by some parabolic subgroup, but we want to just think about them. Sometimes they use this notation: flags space corresponding to A. And right. So for example, for instance, we can use A is 1 1 1 1 1 1 1. This then this complete flags. Flag variety. So that is not studying of just flags is not very geometric because somehow they form there is, yeah. So what we want to do, we want to fix a standard flag and consider all other flags up to transformations preserving a standard flag. So F given by E0, sorry, span of E1, span E1 and E2, and so on, is a complete flag. And we want to understand all other flags in relative position to this flag. So, and more precisely, we can say that we're looking at orbits of B acting on the flag variety. Orbits of B acting on complete flag variety, and then we have a theorem, or in other words, or flags up to B equivalence. Yeah, so I don't know how you prefer to phrase it. You would say that flag F1 is equivalent to F2 if there exists B in B, which sends B. Okay. Then theorem is that there are only finitely many. So FA is only finitely many orbits, B orbits, and they are very easy to parameterize. So more explicitly, that if suppose F prime is a flag, then compute dimension of the intersection F I and Fj, and this collection of numbers is a complete invariant of the orbit. With such collections of numbers, and J are in one-to-one correspondence to orbits. And of course, not all collections of numbers are possible. But, okay, so what do we do with this? And then, right, so how do we compute the deformation of the? Let's define the vector space. We take U F L A. This is modulo B. These are formal linear combinations. Linear combinations of orbits. And this is some vector space which we call dA. So object element in this vector space is just a sum of some flags with some multiplicities attached to them. And now so as you might guess, then VA will correspond to, this corresponds to a line where I put here A1 M in the calculus. And then to construct an algebra action, we just have to say, what do we do with how to interpret certain pictures. And they're very natural.
Can I just clarify a couple of things? So in this, is part of the first statement of the theorem that you have finitely many orbits, even if you work over an infinite field.
it doesn't matter.
Finite set.
Yeah, it's the same finite set for any field. Yeah.
I mean, FLA is a finite set in your.
Also that, yeah, if over finite field, it's also finite.
And then all of the standard flag you chose. How did you use the standard flag you chose? You made this choice of basis.
Okay, I use it because B is a stabilizer of the standard flag. Geometrically, B is a stabilizer of the finite flag. So studying these orbits is the same thing as studying pairs of flags up to simultaneous equivalence. Pairs of some complete flag and some other flag. Right, so this is my vector space. And now the rules of the game is that if I have a this part of a diagram where I have here like AI and AI plus 1, and here it's AI plus I plus 1, and everything trivial is corresponds to the map where you forget map where you have a imagine you have a I, and this is called this A, and this is an A prime. Yeah. So so there is a flag here plus okay, some flag F 0 M, and so you simply forget the steps. Okay, and so that's one map, and then there is another diagram that you may encounter. In this one, it's insert map where you insert in all possible ways. Right, and then the theorem here is that once you put this into, so this gives an action representation of UQ real, and where this is certain information of UGLN of quantum, some quantum. And then, so example, for instance, is that, for instance, EI, it goes to, well, let's look at these two lines that we are supposed to play with. So here, I have to first split this line off and then bring it here. Yes. So there, it's a product of two operations. It's insert. Sorry, forget after insert. And FI is the opposite one. And right, and then, so I'm supposed to probably finish not so late, no?
You started about 15 past, so it's. All right.
No, they're not.
Depends how hungry the audience.
There is a, yeah, the line.
So when you hear the bellies rumble, that's when you know it's time to stop.
Yeah, so what's the another theorem is that now we can do another thing. We can just restrict to vector 1 1 1 1, So it means that if complete flags, and we do the same game, but we have to similarly we will set sigma I to be. Let's first do some computation. Okay, so what is EI? Sorry, what we used this is 1 and 1, and we do something like this, and then we do something like this. So this was FI EI. Now, what is the spectrum of FI EI if you do it now over FQ? So think about it. You have some flag. You forgot one step in the flag, but then you have to insert it in all possible ways. Okay, now what's FI squared? So you inserted something, but then you again forgot it, and then you again insert it. So you simply have to choose q plus 1 elements, which is lines in the two-dimensional space. And so this, you see that this is q plus 1 times fi I, and then sigma I will be fi and I minus identity. Then, so restrict to this, define sigma I this way, then obtain action of a Hecke algebra. So this satisfy Hecke algebra relations, which are sigma I minus 1 times sigma I, or minus q sigma I plus 1 0 sigma I sigma j commutes if they are far, and the braid relation. We obtained in this. Of course, you can say, what you just obtained one representation, right? But so the point is that we can consider some other condition. For instance, we can put some conditions on the flags and so on and so on. We will obtain more representations like this. So, right, in this case, we just obtain Hecke algebra action on itself. So, one remark. So you may think that the theory of GLN representations is more general, includes the theory of SN representation, but it's also true in another way around. The most general theory is more than both of those. It's kind of something you can call GL infinity or S infinity. What do I mean? So we can consider this calculus containing all diagrams, and then to get GLN, which corresponds to this, it corresponds to diagrams with n line. Actually, if you remove all the 0 ones, it's less or equal than n lines. Less or equal than n lines. As n corresponds to diagrams with all thickness equals to 1. One diagram. Now, so they contain all diagrams contain both of these. Okay, so we already have seen how to. It's clear that every SN kind of diagram can be viewed as a GLN diagram, but it's also true in another way, because you can send a partial flag to all possible of its refinements. There's some subset of complete set of plot, of set of complete plots. And this way it gives you some so you can embed all these spaces into one space, right? So this VA is a sub space of V 1 1 1 1 1 1 1, where inclusion is given by sending some flag to all refinements. And so in a way, from here you see that also all like SN representations also cover all the interesting stuff. So, and this is the statement. This is basically the sure while duality. Sure while. Okay, so stop here. So, yeah.